What is a black hole? This is our most recent view of one.
I'm a black hole. I'm a black hole. I'm a black hole. I'm a black hole.
Here, we can observe a theoretical depiction of a black hole and what it would be like to enter the event horizon, as shown in the show Cosmos, A Space-Time Odyssey. Once again, this is only in theory how it would appear if trying to enter the event horizon of a black hole, as the object or person would get sucked almost instantly. They are some of the most compact objects in the universe. A point singularity exists near the center of the black hole. This point depicts a matter density of nearly infinity, showing just how massive all black holes are. Here is a comparison between some different sized black holes and just how massive they can get in relation to our Sun. This first black hole is about the size of Mars. Pay close attention, as this gets mind-boggling. This mid-sized black hole contains about the mass of 1,000 suns, an incredible amount of mass in relation to us. This next black hole is a supermassive one, many times bigger than the previous one. Really pay attention to this one to see just how crazy its mass is. That's right, a whopping 20 billion suns all compacted into that one massive black hole. It is incredibly hard to fathom the sheer mass of that. A black hole forms when a star collapses on its own mass, the beginnings of its infinitely matter density at the singularity. Not much is known of what goes on inside, and nothing is ever able to escape. Not even light. As fast as light is, it can only travel so close without being pulled into the hole. The black hole is able to bend the light as it tries to escape, by shifting the light to a longer wavelength just by its intense gravity. For objects coming close, the most they can travel to is the event horizon, also called the point of no return. Not much is actually known about the event horizon or if it even exists along with the black hole. In fact, they are linked, and if we can find the event horizon, we can prove the existence of black holes. This phenomenon is still being worked on. For the time being, they are expressed as mathematical equations that make sense, but we don't have actual evidence for them, and exist only in theory. Here are a few equations that tell us the properties about them, such as the top two giving us the area of the two horizons comprising a black hole, with the last two depicting mass and surface gravity of the black hole. We won't dive into these and many other equations due to complexity, and we only rely on them as a means to theoretically prove the black hole. The EH, or event horizon, also does the task of separating the interior from the exterior. It prevents signals coming from the inside to reach the outside. The graph here shows a space-time schematic diagram of a black hole with a universal horizon, with time as the y-axis and distance as the x. The green curves represent constant time hypersurfaces as they get darker while moving towards the future towards the top. The red lines span the exterior of the universal horizon, but they don't cross it, and curves spanning the region inside the universal horizon do not extend into the exterior. Consequently, this graph ultimately shows that any signal coming from the interior will not be able to escape the exterior. New radio technology is becoming available that shows the potential of helping to discover and view into the event horizon. Radio imaging technology, however, was unsuccessfully used before in the same attempt, but the closely aligned array of telescopes wasn't able to do much. The new Very Long Baseline Radio Interferometry (VLBI) technique shows promise, however. Before this technique, At most, what we found was fading pulses of light, which are remnants of a light supposedly being sucked into a black hole as its wavelength increased, which was detected by the Hubble Space Telescope. This technique uses an array of specialized radio telescopes. They are placed at incredible distances from one another, ranging from hundreds to thousands of miles apart. It relies on the usage of interference, where multiple light waves are superimposed on one another. The superimposition creates this stacking effect, thus amplifying any signal received by the receivers. This is the James Clerk Maxwell Telescope, and is the world's largest radio telescope. It was used as one of 3 telescopes to detect radio signals coming from the center of the Milky Way galaxy, possibly from the black hole called Sagittarius A. The graph here shows how the width of Sagittarius A was determined from interferometric observations of 3 spread radio telescopes. For a pair of them, the correlated flux density, a measure of the interference pattern's clarity, is plotted against the projection of the separation from the line of sight. The width is estimated from fits of simple models of its shape on the sky to measurements on the green and red baseline. The technique has successfully obtained resolutions 1,000 times sharper than the Hubble Space Telescope. It has also been credited for finding the echo of the Big Bang, which is now known as the cosmic microwave radiation, as well as detecting the first pulsar stars. While not fully tested yet, it shows great promise as it can truly lead to the possibility of finding the event horizon, and perhaps even allow us to explore further past the event horizon and in the black hole.